I'm Uma. I'm one of the co-founders of Succinct. In general, we're focused on like how ZK snarks and starks can help improve like blockchains. So kind of like a big current application of ZK in blockchains is ZK for scaling. So think ZK EVM or ZK rollups. And at Succinct, we're interested in like other use cases of ZK, including ZK for interoperability, so to make interoperability more secure. And we're working with the Avail team to make a ZK bridge for Avail, the ZK data attestation bridge that will let Avail state be bridged to Ethereum. Currently today, like it's helpful to understand the current interop landscape, which is mostly like generally you have two different chains with two different consensuses, and you want to like verify something happened on one chain and then take actions on the other chain. And generally most interop protocols today work by having like a small multi-sig or a small group of trusted entities that are responsible for attesting to the state on one chain and then taking actions on the other chain. So for example, oh, a burn happened on chain A, let's do stuff on chain B. And obviously I think multi-sigs have a few problems, like it's a small group of trusted entities, they are insecure, they can get hacked, there's like a lot of multi-sig hacks. And so like kind of one of the best ways to do bridging is to directly verify the consensus of chain A in the execution layer of chain B. So directly verifying the consensus of chain A in a smart contract on chain B, to be more specific. Now, generally that's hard because like verifying consensus is an expensive operation. You have to verify a bunch of signatures. You have to verify a bunch of hash functions. And so that's generally not well suited for like the really computationally expensive blockchain environment. And so what we do is we take ideas from like ZK that's generally used for scaling blockchain computation, and we apply it to scaling verification of consensus. So we generate this like ZK proof, we call it ZK proof of consensus, where we have the succinct proof that like all these validators signed off on like a particular state of the world, a particular header, and we verify that in a smart contract on another chain. And then with this proof of consensus, you can just like natively have the chains talk to each other without the need for some like intermediary in the middle. So for some more context, previously, so Succinct's first protocol is Telepathy, which uses a proof of Ethereum consensus, in particular proof of Ethereum's like client protocol, the sync committee, and it basically verifies the signatures of Ethereum's like client protocol in a snark, and then we can verify it on any chain. So you can like basically get Ethereum state on any other chain. A circuit is just like a statement, it's just a unit of verifiable computation. So we have this function that's like basically verify signatures, and we take in all the Ethereum validator signatures. Actually, we take in one aggregate signature. We verify that they've signed, and then we verify they've signed a particular block header. And then what happens is we update a smart contract over here. So we have a smart contract in Solidity that lives on other chains that can verify the proof. So it verifies the proof, and then it like does a bunch of stuff, and then it keeps track of the block header. So it's a really simple on-chain like client. So this proof goes into this smart contract here. And then as I was discussing, like this ZK proof of consensus, the proving scheme we used was Grot 16. And then in particular, like the language we were using to write these circuits was Circom. So that's kind of like the whole pipeline for Ethereum proof of consensus.
So first of all, for like safety, like there is essentially is trust in that sense, right? Because like, we're essentially using, like the taglines that we're using math to verify, to verify that all the Avail validators have, essentially signed off on it. But you do bring up a good point that like, so if it is down, then essentially like liveness of the system is kind of halted. Definitely not the Avail blockchain, but of the updating of this smart contract. Yeah. So there's a few things that we do to mitigate that. So one is that like our operator, it does kind of have a sync mode. So like every time it starts up, then it knows that it has to, it'll read like the latest head from the smart contract and go ahead and kind of resync from where from where that left off to the actual head. And given like some of our pretty performant like proof constructions, then like that shouldn't be too bad to have to resync. The other thing is that we plan to make these all like redundant. So this is kind of going into more like I guess like more traditional Web 2 engineering problems of like making sure the uptime for each of them is high and whatnot. But I think the cool thing is that you can. I mean, this design is like it generally follows like kind of like a microservice design. So just having like simple like replicas for these like RPC these RPC servers, that's generally pretty trivial to do. And putting them behind like a load balancer. Yeah.
Hi, I'm Anurag, co-founder of Avail, and this is one of the first Avail Whiteboard sessions. And today we have Uma and Kevin from Succinct joining us, and they'll be talking a little bit about the work they've done previously, but more details on the Avail data attestation bridge that they're building from Avail to Ethereum. So welcome Uma, welcome Kevin. Uma, if you can give a brief intro.
Yeah. I'm Uma. I'm one of the co-founders of Succinct. In general, we're focused on like how ZK snarks and starks can help improve like blockchains. So kind of like a big current application of ZK in blockchains is ZK for scaling. So think ZK EVM or ZK rollups. And at Succinct, we're interested in like other use cases of ZK, including ZK for interoperability. So to make interoperability more secure. And we're working with the Avail team to make a ZK bridge for Avail, the ZK data attestation bridge that will let Avail state be bridged to Ethereum.
Cool. So Uma, can you talk a little bit about your previous experience, because you guys have built the Telepathy Bridge. So maybe a short introduction to that would be helpful in understanding the context as well.
Yeah, so currently today, like it's helpful to understand the current interop landscape, which is mostly like generally, you have two different chains with two different consensuses, and you want to like verify something happened on one chain and then take actions on the other chain. And generally, most interop protocols today work by having like a small multi-sig or a small group of trusted entities that are responsible for attesting to the state on one chain and then taking actions on the other chain. So for example, a burn happened on chain A, let's do stuff on chain B. And obviously, I think multi-sigs have a few problems, like it's a small group of trusted entities, they are insecure, they can get hacked, there's like a lot of multi-sig hacks. And so like kind of one of the best ways to do bridging is to directly verify the consensus of chain A in the execution layer of chain B. So directly verifying the consensus of chain A in a smart contract on chain B, to be more specific. Now, generally that's hard because like verifying consensus is an expensive operation. You have to verify a bunch of signatures. You have to verify a bunch of hash functions. And so that's generally not well suited for like the really computationally expensive blockchain environment. And so what we do is we take ideas from like ZK that's generally used for scaling blockchain computation, and we apply it to scaling verification of consensus. So we generate this like ZK proof, we call it ZK proof of consensus, where we have the succinct proof that like all these validators signed off on like a particular state of the world, a particular header, and we verify that in a smart contract on another chain. And then with this proof of consensus, you can just like natively have the chains talk to each other without the need for some like intermediary in the middle.
Yeah, okay, makes sense. So that was telepathy, and so that provides some context for like what we are about to kind of discuss over the next few minutes. In general, so before getting into the data attestation bridge, I just like to introduce validiums, right? Like or optimistic chains, or like constructions on L2 where data availability is done off-chain on a layer other than Ethereum. And so, for example, for validiums or optimistic chains that do data availability on Avail, it is important that we attest to data availability guarantee on Ethereum via some means, right? And so that was the rough requirement that we discussed with Succinct, and in the sense, how could we solve this problem for Validium constructions for optimistic chains. And now, since there are a lot of L3s now coming into the picture with all the major L2s bringing one-click deployable stacks, right? Like, so the need for those kind of constructions is going to grow only higher, right? Like, and so that is the context in which we approached Succinct, and they helpfully agreed to work with us on that, right? Like, and so what was in your mind, Uma, Kevin, like when you're first thinking about approaching this problem of, because this was a different consensus scheme, and like some trade-offs, and which we'll get into more detail later, but what was your first thought on like listening to this problem at first?
Yeah, I think so. For some more context, previously, so Succinct's first protocol is Telepathy, which uses a proof of Ethereum consensus, in particular proof of Ethereum's like client protocol, the sync committee, and it basically verifies the signatures of Ethereum's like client protocol in a snark, and then we can verify it on any chain. So you can like basically get Ethereum state on any other chain. And then it's also useful for cases where there's many chains that in the case there are chains that use Ethereum's consensus. One example is Gnosis chain. Then you can do bidirectional bridging between both of them. And so with our Ethereum ZK Lite client, we can actually, we're actually live today in integrating and validating the Ethereum to Gnosis bridge. So we like our proof of consensus helps secure that bridge. So when Anurag and the Avail team came to us and explained they also wanted like a ZK based solution for a secure Avail-like client on Ethereum to get Avail state on Ethereum. The main challenge there is like the consensus algorithm they're using is different than Ethereum's consensus. So in particular, I believe Avail is built on this Polkadot substrate SDK. So they're a substrate-based chain. And yeah, it uses this grandpa consensus algorithm. And that's a bit different from Ethereum. I think at its core, it's like has similar ideas. Like you have validators, they produce signatures, and you have to verify 2/3 of the validators have signed on a block header. So at a very, very high level, it's similar, but the details are different. So for example, Ethereum uses this BLS signature, which is an aggregate signature. And to commit to the validator set, to know who's actually a validator, you use this SHA hash function. I think the Avail chain is built on Substrate, which has ED25519 signatures. So it's like a different curve, a different signature compared to BLS. And then the hash function that they use to commit to the validators is Blake2B, so it's like slightly different from SHA. And so, yeah, basically like at a high level, the algorithms kind of look similar, but then the actual primitives for verifying signatures and verifying the hash function are different. And so, yeah, we had to build basically new primitives for that. And I think the other main challenge is Ethereum uses this signature scheme called BLS. That's really, really nice because it's an aggregate signature. So basically, if you have, let's say, 1,000 validators that sign a BLS signature, in the end, they actually produce one signature for all 1,000 validators. And you can check all 1,000 people sign the same message by verifying one signature. It's like a pretty nice, relatively newer technique. Whereas Substrate uses ED25519 signatures, and those aren't an aggregate signature. So you have to verify like 1,000 separate signatures. And so ZK is generally pretty like expensive computationally. There's generally a large overhead of verifying these operations. And so we had to develop like a few new techniques to basically efficiently verify a lot of these signatures at once. And so that was like one of the main technical challenges with like what we ended up building.
Okay. So before getting into the concrete specifics, right? Like, what are the technology stack that you use for Telepathy Bridge, and what changes did you have to do for this bridge project?
Yeah, that's a good question. So for Telepathy and the Ethereum ZK Lite client, we used this protocol, the ZK Snark protocol called Groth16. So this one has been around for like a very long time. It's and then there's like several different like DSLs or like ways to program circuits in it. So in particular, the language that we use to like write the circuit is called Circom. Circom's been around for a while. It's actually like, for example, the circuits used in Tornado Cash, which is probably one of the most popular ZK protocols live like on mainnet. are written in Circom. So it's been around for a long time. It's been like fairly battle tested. But at the end of the day, Grot16, since it's an older protocol, is like pretty simple in a lot of ways. So it's not like super it's not very, very performant. So because for the Ethereum Light Client protocol, it is more simple and you have this aggregate signature, we were able to use Grot16 and write it in Circom. And still our proving time was like 2-ish minutes, so it's not that bad. But for something like Avail, where we have to verify potentially thousands of validator signatures that are ED25519, Grot16 would not cut it, like it would not be performant enough. And so we have to like adapt our tech stack and move to something that supports recursion and like is more flexible. And like more, it's a newer proving system, so basically it's more powerful. And it has like these newer techniques. So in particular, what we ended up doing was we used this framework called Plonky2, developed by people at, now they're part of Polygon, and they're building a ZK EVM in it. But basically Plonky2 is really nice because it's this Stark-based, I guess. Plonky2 is this framework that has like access to more powerful new cryptographic primitives and like a new powerful ZK protocol. And actually it has a Stark-based protocol in its framework called Starky that we used. That's like, we are able to really optimize it for verifying signatures. So we ended up actually combining a bunch of different proof systems. So we used Plonky2 and Starky to verify the signatures. Also, Plonky2 is really nice because it has recursion. So you can generate proofs for all the signatures in parallel, and then you can recursively verify them. And so that gives you like really low end-to-end latency. And then the final thing we have to do that was like technically difficult is the trade-off with Plonky2 is that the proofs it produces are much larger than Grot16 proofs. And so it's not really feasible to verify these proofs in EVM. So we had to basically have a final wrapper Grot16 layer on top of these Plonky2 proofs to actually allow for like succinct, efficient verification in EVM. So that's probably like a lot of words, but basically at the end of the day, what we had to do was upgrade to like a more advanced proving system and then compose it and aggregate with like Grot16 to get the cheap on-chain EVM verification. And so in that, it was like a lot more technical primitives to do this new consensus protocol.
Great. Awesome. So in general, I think that, now we're ready to get into the meats of it, right? Like, so maybe we can use the whiteboard to kind of draw out the entire architecture once, and then we can slowly get into it one by one. So probably, do you want to kind of start with, like, will you do it? Will Kevin do it? Like, do you want to start with the architecture?
Yeah, I can maybe start with the high level, like all the different proof systems, and then Kevin can go more into the specifics.
Okay.
So at like the highest level, we have, or maybe it's helpful to like our old system, to just outline our old system versus our new system. Maybe that's like interesting. So yeah, our old system, this is Telepathy, which is our Ethereum Light client in a ZK snark. So this one's really simple. You basically have like Ethereum over here. It's kind of a poor Ethereum logo. And you have these Ethereum validators that are producing signatures and block headers. And then what happens is we just like watch for these signatures and block headers and other artifacts of consensus. And then we generate this like ZK proof of consensus. And we just, so each ZK proof is just a statement. So a circuit is just like a statement. It's just a unit of verifiable computation. So we have this function that's like basically verify signatures, and we take in all the Ethereum validator signatures. Actually, we take in one aggregate signature. We verify that they've signed, and then we verify they've signed a particular block header. And then what happens is we update a smart contract over here. So we have a smart contract in Solidity that lives on other chains that can verify the proof. So it verifies the proof, and then it like does a bunch of stuff, and then it keeps track of the block header. So it's a really simple on-chain like client. So this proof goes into this smart contract here. And then as I was discussing, like this ZK proof of consensus, the proving scheme we used was Grot16. And then in particular, like the language we were using to write these circuits was Circom. So that's kind of like the whole pipeline for Ethereum proof of consensus. For Avail, the diagram is pretty similar. So I'll just swap in the relevant parts. So here you have Avail. Now actually the end-to-end flow looks very similar. Like the Avail chain is producing, the validators of the Avail chain, they're producing signatures and block headers as like artifacts of consensus. And then we take a look at those signatures, and then we produce the ZK proof of Avail consensus. Now the difference here is actually this part gets a lot more complicated. So to zoom in, initially what we do is we have like a bunch of signatures. So we have like an ED25519 signature here, and we have, in the future, there might be like hundreds or thousands of them. So we have a bunch of different signatures. And then we put all these signatures into our like Starkey proving system. So we have one Stark that verifies a batch of signatures. So this goes into our Starkey based signature verifier circuit. So we have one circuit to just like verify signatures. It's like highly optimized for verifying signatures and for doing all this computation. Then we put that into a Plonky based verifier to like verify the rest of the computation associated with verifying, let the validators have signed off. So there's like some other logic you have to do. And again, I'm like keeping it pretty high level. I think Kevin will go more into the details. And then finally, like these things, they generate a proof, but the proof is pretty large. So like it's really big. And then we have to put into this like Groth16 wrapper. So one cool thing about ZK is that like a ZK circuit is just a function. So you can verify a ZK proof in a ZK circuit. This is a concept known as recursion, and it's really powerful because you can compress like an arbitrary amount of computation in one circuit. So like you can verify other ZK proofs, you can generate a bunch of them in parallel, and then you can aggregate that. You can verify like a lot of these proofs and aggregate them, and you can recursively verify them. So that's how you compress a bunch of computation using recursion and aggregation. And so we apply that technique here like a few times. Like first we generate a bunch of these signature proofs in parallel, then we recursively verify all of them and aggregate them, and then we take those proofs and we recursively verified it in this Groth16 wrapper to get it to be more compressed for on-chain, and then we send that proof to this on-chain smart contract. So as you can see here, the Avail pipeline's like far more complicated than our previous one. Like we have these 3 different proving systems, we're combining all of them together, and then we can send it on-chain. But the smart contract looks like pretty similar at the end of the day. Like you verify a proof, you store the block headers, you store a commitment to the validator set so that you know who the validators are, so you know like whose signatures you care about. But yeah, that is like the end-to-end kind of flow of the Avail data attestation bridge.
Okay, cool. And there are some off-chain actors as well, right? Like in sending this to the contract, right? Like I mean, is there anything specific you want to say about it, or is this just a relay channel sort of a thing?
Yeah, you have to, like, I think the off-chain actors involved in like coordinating all this stuff are complex because you have to kind of manage this like proving pipeline and this recursive proving pipeline, and then you have to like be responsible for sending these transactions. So yeah, the off-chain actors who are involved in this like have to be responsible for managing a lot of computation and then like sending it on-chain and relaying it when like a new proof is needed. So say if Validium needs, wants to settle to Ethereum, they would signal like, hey, I want a proof, and then it would like get verified. Yeah. Okay, makes sense.
And in general, was there anything specific to Avail, for example, that necessitated changes here, which might not have been present in Telepathy? Like things like, so initially I remember we talked about doing like the data root verification, for example, but at a certain point we also we're thinking of commitment verification of the which were there in the header, but like of course we went ahead with that. So maybe some if you can throw some color on that. Did it add to the complexity a bit?
Yeah, I think in general there's always like some differences. This at the end of the day is kind of like an on-chain like client for Avail. So because the consensus protocol is a little different, there's always like a little bit of differences. In general, we try to wrap as much computation in the circuit as possible because that means the on-chain gas costs are reduced. But of course, there's still some changes, like for example, your commitment to the validator set has to be a little different. Or there's like some things that are like easier to put in Solidity than in the circuit. So I think, for example, there's like some hash functions for like storing the validator serializations or something like that Kevin can speak to that are currently in the Solidity smart contract because they're not that gas expensive, and it's annoying to put in the circuit. So yeah, there's like some changes that we did to the smart contract. I think Kevin knows a lot more about them.
Okay. Makes sense. And to this architecture here, right? Like in terms of batching different SIGs here, right? Like what was the main rationale? If you can just let our audience know, right? Like why is it not possible to do? Of course this is expensive, but in general, if we can get into the approach there.
Yeah. So like as I was saying for Ethereum, there's like one aggregate signature called BLS. And so with a BLS signature, you just have to verify like one equality to make sure that these validators have signed, or some subset of people have signed. So that's quite nice. Here, like you might have, I think Avail eventually wants to have thousands of validators in the limit. So you have like these thousands of signatures. And the signatures, because there's thousands of them, like perhaps each individual one, I believe like, if you just verify one signature in Graph 16, it'll probably take like 10 to 15 seconds to generate a proof of that signature. So if we have thousands of signatures, but we want to verify it for each header, that quickly becomes infeasible because, well, you have like that 10 seconds times 1,000, and that's just like not feasible. So if we want to reduce the end-to-end latency, we have to verify each signature individually in parallel, and then we can basically recursively verify all the proofs. So like a diagram that's kind of useful to think about here is like you have this structure where you have a tree of computation. So each leaf in this tree is a signature. So this is like sig1, signature 2, etc. So you have all these signatures. We generate proofs for each of them in parallel. So maybe each individual proof is like 10 seconds, but you're able to do this in parallel. So overall, like to generate all these proofs is only 10 seconds for all of them because you're doing it in parallel. And then you use recursion to basically generate a proof that these two proofs are valid. So you generate a proof that, for example, signature 1 and signature 2 are valid. And you generate a proof like this and generate a proof like this. And this is like very overly simplifying. Like in reality, what happens is here each leaf is actually a batch of signatures. So we'll actually verify like 10 signatures or something like this in each leaf, and then we'll aggregate a bunch of them. So like this proof might actually be attesting to like 20 signatures at a time, or maybe like even more than that. But basically then you verify this. And like the nice thing about ZK circuits is to verify this proof is actually like a much shorter computation than verifying a signature, because ZK can be thought of kind of as like computational compression. Like you're compressing the function verification into like a more succinct statement. So here, like verifying that these two proofs are valid is actually much less work than verifying each individual signature. So that's kind of like the power of recursion. So then generating these proofs might take like 1 second each, and then you just like recursively do that in the tree, so that takes 1 second. And then you finally get one proof at the top that says like, okay, my 1,000 signatures are valid. And in overall, the end-to-end time is just like adding up each level. So it might end up being, it's like log basically the number of leaves that are there, plus like the leaf cost. So in general, it's actually, the end-to-end latency is actually quite fast because of this recursion. And yeah, the reason we do this is, again, just like reduce end-to-end latency for verifying a bunch of signatures. And then there's also like a lot of tricks we had to do at this level that Kevin can talk more about, where to verify a batch of signatures, to make this go down to 10 seconds is actually also pretty difficult. So we had to do a lot of optimizations, even just at like the verifying batch of signatures level. So it's kind of combining like a bunch of techniques like recursion and then optimizations here to get the end-to-end latency of 1,000 signatures in parallel down to like something that's manageable.
Yeah, that's pretty useful. So now I think we have the lay of the land in terms of the end-to-end architecture, right? Like, I mean, so essentially to summarize, right? Like what we are basically doing is what Succinct has done is taken the consensus that the Avail chain follows and created an optimized circuit for proving the consensus. They have a set of off-chain actors that then relay the proof to a set of Ethereum contracts that can then verify the proof and then basically prove things like data root inclusion and stuff like that, right? Like, and so that is particularly useful for validiums and optimistic chains which want to understand whether the data is available on Avail via an Ethereum contract. So in general, when we started the project, right? Like we had started thinking about it from a bidirectional point of view, but initially we started it off in a one-way kind of a thing. Any thoughts around how this could be bidirectional in nature?
Yeah, so you can take our existing Ethereum-like client and then verify it in the Avail smart contract layer, or if Avail doesn't have smart contracts, like it could be a system program in the Avail runtime that verifies our Ethereum-like client proof, and then it can have the Ethereum state, which might be useful for like maybe bridging Ethereum information to Avail. And so yeah, you can have ZK proof of consensus of Ethereum verified in the Avail runtime, and then we have an Ethereum smart contract that verifies Avail proof of consensus, gets the Avail state, gets attestations to what data is available on Avail, and then you can make it bidirectional that way.
Cool. Makes sense. So should we now start getting into a little bit of the detail?
Yeah.
Thanks Kevin for joining. Kevin, maybe before we start, can you give a brief introduction of yourself?
Yeah, so I'm one of the engineers at Succinct, and I've basically been focusing on building out much of the ZK circuits and some of the off-chain actors for the Avail attestation bridge.
Cool. Thanks, Kevin. So I think at this point in time we have the end-to-end architecture in place, right? Like, so maybe we can just get into the meats of it in terms of the circuits, right? Like, I mean, so from your point of view, right? Like, I mean, what were the challenges you faced in general from like understanding how the consensus worked, for example? Like, basically, how did you arrive at the final design document? Like, if you can take us through that.
All right. So as Uma kind of mentioned, at the very high level, like what we're trying to do is that prove via ZK circuits that a set of headers has essentially been signed off via what's called a grandpa justification by the Avail validators. So I can first start off on what are basically kind of the inputs into the circuit. All right, so first of all, these are all like taken from one of our existing like off-chain actors, which we call the operator, and it's basically listening to to an Avail like full node, retrieving new headers, and then retrieving a justification of the headers, which will then prove that basically the headmost block is finalized. So here we have the headers.
Yeah, and just to like add here that grandpa is slightly different in the sense that it finalizes range of blocks or chains rather than individual blocks. So I think that also Kevin will cover.
Yeah, so as Anurag mentioned that when a justification is received, the contents of it would be basically a set of signatures from the validators. Basically, this set should be of size of the quorum, so basically 2/3, and as well as signing off on not a single block, but actually on a subchain what basically which is a sequence of blocks. So that presents some challenges in terms of the circuit that we have to build. I think namely that what it is signing off on is essentially kind of a variable size data structure versus like just one like block hash. All right, so now that we kind of have the inputs into the circuit, then I can kind of start describing some of the high-level components of our of the circuit itself.
Yeah.
All right, so first of all, we have kind of like a IVC-based header validator. So what this is that it takes in and we actually are using this kind of sub-circuit in two different places. So one is to parse this subchain or sequence of blocks, and the other one is to also parse the actual finalized headers that we want to eventually put into the smart contract-like client. And basically, what this does is that it will so IVC it's basically kind of like it's a design pattern where the inputs into the circuit is in our case like every single specific header, but then also a proof that the previous header has been it's valid. So you can think the inputs are like a header and then like basically a proof that like the previous header was like valid, so h minus 1, and this is at header h. So this is inputted into the circuit, and then then this will output a proof saying that proof h, basically, and what this proves is saying that like all basically the subchain that ends in header h is valid. And then this can then be fed in, essentially kind of fed in back again.
So basically you're looking for and listening to all the headers and the justifications in general. Mm-hmm. And because these are subchains, right? Like, I mean, mm-hmm. the fact that something at block h was finalized, mm-hmm. that means like if the previous justification was h minus 10, mm-hmm. and you received h as a justification, mm-hmm. and when you prove it at height h, that means all the blocks from h minus 9 to h were finalized.
Exactly, yes. It'll do essentially 10 iterations of this. Mm-hmm. And because we're using Plonky 2, which has like great recursive properties, mm-hmm. This can be done really, really quickly.
Okay.
All right, and another piece that I think it'll be interesting to go through is basically the signature verification. So I think Uma did kind of touch upon this a little bit, but one of the challenges that we have to face with the Avail circuit is that we now have to like verify up to 1,000 signatures, and that's multiple orders of magnitude more than our original like telepathy, where we only had to verify one. So how we did this is through actually a combination of methods. So doing it the naive way, we essentially can create this one large circuit. Okay, so imagine that each of these are little sub-circuits. And each of them would be EDD, SA verification. So we can essentially create this one large circuit that will verify 1,000. But then, that'll run into a few problems that this is going to take a very long time to generate proof, and then most likely, especially if we're doing this with GRA 16, most likely we'll kind of hit like their hard limit. So instead, what we're doing is that we are creating a circuit that will, a Stark-based circuit that will verify these in parallel. And specifically, it will do 256 in parallel.
Okay.
And just to kind of go into the bit of the details, so what our Stark circuit is doing is that is verifying scalar multiplication. So scalar multiplication is essentially the most complex operation within a signature verification itself. All right, so basically, yeah, within a Stark, you will have, you can kind of imagine the layout of the circuit or the trace is, essentially one big matrix. And let me kind of take one step back. So as I mentioned, like what we're doing here is doing essentially a parallelized like scalar multiplication verification. And what this operation is basically an elliptical curve point times a scalar. And this is the result. So what we're doing is that we are fitting in, like, okay, and these are like, rows of 256 or batches of 256 rows. So what we're doing is that each one of these batches, we're doing a single instance of this verification. And how this works is that we are basically filling out like the initial elliptical curve in this first row here. And then for the scalar, we're basically bit decomposing it into 256 bits. So the scalar would essentially kind of look like this. And then there's kind of this well-known algorithm called like double and add, okay, which is used, for this scalar mul. And essentially what happens is that, okay, so we'll have a whole bunch of ones and zeros here. That this column is going to essentially act as a selector column, and so basically where it is 1, then it would essentially know that it needs to double it, and where it is not, then it won't, right? So then at the very end, then you'll get the kind of the result of this of the operation, okay, right? And then basically we also have another column which we call like the aggregator column, which will then essentially sum up the calculated result, but then sum it up with some randomness. So then we'll have I guess the final aggregated one right here, and then from here we can essentially witness what we believe the result is, and then that when we sum up the aggregated our aggregated witness, then it should match the final aggregated one that's calculated within the circuit.
Okay.
Yeah, and then so basically, like I said, this is each chunk here is 256 rows, and then we have in total 256 chunks right here.
Okay.
And I mean, just to kind of give some performance numbers here. So, so doing this would take like a minute and a half, mm-hmm, right? And that's 256, right? So if you kind of just divide by whatever, it's around I think 30 milliseconds.
Mm-hmm.
Oh, sorry, 300 milliseconds. We'll get it to 30. All right. Cool. So I think, okay, so those are two kind of sub-circuits of our, of the Avail circuit itself.
Yeah.
All right, and then, okay, so here we have our, the header validator, and then we have our signature validator. And then we kind of basically have this might be using succinct terminology, but this is what we call the step circuit. Mm-hmm. And this is using Plunky too. And basically within it, it has verification for this subcircuit and then this subcircuit. So we'll basically run this every time we want to update the light client. And then this will be fed into what we call a normalization circuit or normalizing circuit.
Or a step circuit.
So this is okay. So this is also Plunky too. But basically, what this does is that it takes. So it would produce a Plunky 2 proof that is basically like a common size. So or let me take one step back. So the resulting Plunky 2 proof is essentially dependent on like many other many factors.
Yeah.
And not only that, the resulting size or the custom gates it ends up using will be different among different, let's say, application circuits.
Okay.
So what this does is that it will create a constant size proof plus using the same set of custom gates.
Okay. So basically, this circuit is verifying that circuit, but outputting a constant size proof.
Exactly.
Okay.
Yeah. And then this is fed into our proof compressor, basically. So this is our raw 16, which we're using Gnark for.
Yeah.
Proof compressor. And then this will then output a very, very small proof, which is then basically an EVM compatible proof.
Yeah. Or EVM, cheap to verify on EVM.
Yeah, exactly. Yeah. So only like 350K gas.
Cool.
Yeah.
In general, so when we think about this, the signature verification complexity of 1,000 validators and this justification height, block height. So of course this is abstracted, right? But can you just spend a little bit time on the complexity? What is being done from compressing it? Because I'm assuming you're parallelizing it as well.
Yeah. So okay. So the cool thing about this is that we can how can I say this? So we can update this recursive proof as we download each single header.
Okay.
And right now, the plan is that we're going to submit a step update transaction for every 20 headers. So we can essentially be doing work while we're downloading all the intermediate headers. So that's one thing. For this one, as I mentioned before, that even on one machine, it can handle a large amount of signatures. But it is very parallelizable. We can pretty almost trivially just run these across a fleet of machines, and then and then we can then use what Uma kind of mentioned about this tree-based, recursive data structure.
Okay, makes sense.
Mm-hmm.
Under current benchmarks, right? How many signatures are you able to prove within what rough time?
Mm-hmm. Yeah. So with the Stark-based one, so with 256, it is a minute and a half. So that would roughly equate to 300 milliseconds per signature.
Okay.
Yeah.
So roughly, if we were to have like 1,000 validators on Avail eventually, so at this current implementation, even on a single machine, this would be roughly taking 6 minutes, which is fair. Which is quite good, because in the context of Avail, right? Like, I mean, Validiums, like, they don't have to have real-time guarantees of, like, we don't have to be attesting to Avail blocks every Ethereum block, right? Like, I mean, we are generally, it is the fact that, like, it will be in the order of minutes or hours where we send an attestation, but that attestation attests to a range of blocks on Avail. And so that's why this is, I mean, this is great work. But like, we would have been happier with even less, like, or more in terms of. But I mean, this is absolutely great. And just to bring home the fact that this is parallelizable, so if we wanted to, this could be like done in maybe 1.5 minutes if we run 4, for example, instances or whatever, right? I mean, in general, right? Like, so. Yeah. So yeah, I mean, I think that's cool. In general, maybe let's talk a little bit about the off-chain actors, and then we can get to the contract bits.
Okay.
Do you want to, is there anything else you want to cover here? Okay. So maybe then move before, like, sorry, I asked to move, but any kind of things that you had started with, like in the technical design, and you had to refactor or change the design for when you started with and where you are currently now?
First, like, we essentially had kind of the naive design, right? So we first, the first iteration did not have an IVC based like header validator. It just essentially took a batch of headers, like 20 headers, and validated all within one circuit, and the same with the signature. And I think it was okay for the first like Avail testnet, just because it had like 10 validators. So we essentially had like I said, the naive design of just having every, like all the EDDSA signature validations just kind of like inlined in one circuit. And honestly, the timing there wasn't too bad. It was, I believe that like the time to generate a proof for 20 headers was about 3/4 of the time to actually, like the Avail chain to actually mine like 20 headers. But of course, that's only with 10 signatures. So like where the blockchain will eventually head to, that that by far would not like be performant enough. So so I mean, that's why we had to come up with this batch like Stark verification circuit for the signatures. Okay. All right. So for the off-chain actors, so there's basically 3 main components to it. Okay, so let's start off with like so here's like an Avail node, right? Which obviously is not like our off-chain actors, but our one of our actors will be connected to it. So here's the Succinct operator, which will basically be listening for like new headers. And then it would also be listening for justifications. Justifications. So once, so basically this operator will batch like headers as it collects them, and then as I mentioned, then it can, like, while it gets a new header, then it can just generate a kind of an incremental header verification proof. And then like either after, so then we'll have like a minimum batch number. So once it hits that minimum batch number and then gets the justification, then it'll go ahead and kick off the proof generation. And so there's kind of one nuance here is that, so for Substrate, there's no guarantee that you're going to get a justification for every block. So sometimes we might have to wait longer. And I think I do want to kind of point out that that does lend itself well to our kind of IVC-based header verification. All right, but once the succinct operator gets the batch of headers and the justification, then it'll go ahead and make an RPC call to basically what we call our step proof generator RPC. And here it will basically send the signatures, header, like the subchains of what they're assigned, all that information. Essentially, this is like the proof inputs. And then it will go ahead. So this actor will go ahead, kick off like the IVC proof generator, the Stark proof generator, and then generate the step proof, and then normalize it. And then this will be essentially the normalized step proof. And then we have basically another RPC, which is our proof compressor. And again, this is Growl 16, Gonarch. It would send over the normalized step proof. Then it would generate like basically the Growl 16 proof. And then, so here's like, let's say the Ethereum smart contract. So the ETH like client smart contract, and then it would just go ahead and then submit the proof along with so the Growl 16 proof, along with so essentially an array of so block number. So I'm not going to write all the fields, but
yeah.
So, but block num and a whole bunch of other like individual fields within the headers. So, for example, like the Kate commitment, the state root. So it would have an array of that, and then basically the smart contract will essentially kind of hash up this. This is actually going to be pretty big, but it's just going to hash that up. And then feed that like commitment into as part of the input into this Growl 16 proof. And then once it verifies, then that is essentially attesting to the statement that a quorum of validators have signed off on headers with with headers that have these fields. And then I'll go ahead and update the smart contract.
Cool. No, certainly makes sense. Okay. In general, so now we have a full idea of how the circuit is created and what are the option actors and what is submitted to the Ethereum smart contract. Here, there are things like the commitments and the data root, for example, which the validiums can query for inclusion, for example. So specifically, validiums, when they submit the data to Avail, that they can verify inclusion via the data root that is submitted here, and so that's one of the main purposes of this bridge, right? Okay, so in terms of the entire construction from a trust assumptions point of view, right? Let's assume, what are the trust assumptions in this setup? What happens, let's say, at the worst case if some of these off-chain actors are down, for example, and so on, right? So maybe let's just talk a little bit about the trust assumptions, in this entire construction.
Okay. So first of all, for like safety, like there is essentially is trustless in that sense, right? Because like we're essentially using like the taglines that we're using math to verify to verify that all the Avail validators have essentially signed off on it. But you do bring up a good point that like so if it is down, then essentially like liveness of the system is kind of halted. Definitely not the Avail blockchain, but of the updating of this smart contract. Yeah. So there's a few things that we do to mitigate that. So one is that like our operator, it does kind of have a sync mode. So like every time it starts up, then it knows that it'll read like the latest head from the smart contract and go ahead and kind of resync from where from where that left off to the actual head. And given like some of our pretty performant like proof constructions, then like that shouldn't be too bad to have to resync. The other thing is that we plan to make these all like redundant. So this is kind of going into more like I guess like more traditional Web 2 engineering problems of like making sure the uptime for each of them is high and whatnot. But I think the cool thing that is that you can, I mean, this design is like it generally follows like kind of like a microservice design. So just having like simple like replicas for these like RPC these RPC servers, that's generally pretty trivial to do. And putting them behind like a load balancer. Yeah, and then I mean we could also do some interesting stuff with the operator. I think the cool thing is that even if you have replicas and let's say we forgot like one is running, or I don't know, or maybe some other like third party is running it. Like the cool thing is that like when this is updated, that this proof itself and just like the transactional nature of like Ethereum transactions would always make sure that the data within this would be consistent. So there will never be like, let's say like redundant data for block headers or even like ones that are conflicting.
Cool. So I think basically from a Validium point of view, I mean, checking for data validity is might be late because if the infra off-chain actor infra goes down, but it'll never be like there's no safety issue ever, right? Like it's just that checking for it might be a few hours or a few minutes late, right? Like but otherwise, and this architecture is also able to move into probably a permissionless setting if possible, right? Like I mean we maybe in the first iteration not, but certainly we don't. This can lend itself to a permissionless off-chain actor architecture as well. Correct?
Yes, exactly. Yeah, I mean we can maybe throw in using like our own consensus algorithm for let's say the operator. Then you can have like essentially the decentralization piece of it, which should solve like for the liveness problem.
Makes sense. So I think basically we've gone through the end-to-end overview. We've gone into the details on the circuit, the flow, on the off-chain actors, and we've touched on this smart contract. Maybe like Kevin, do you want to add anything to the smart contract specifics, or is just so we're just putting the data there and we are proving inclusion there? Anything else you want to add?
Sure. Yeah. So one thing I didn't really touch on too much is what we call the rotate transaction. So this is when like the validator set changes. Okay. Yeah. So pretty much all blockchains have this, where like after like a certain set of blocks or what's called an epoch, then the validator set will rotate. So it could be the result of let's say like a validator election or whatnot. So you can think of like the Avail blockchain is just go ahead and mining blocks, and then once it hits the epoch, then it is going to have a validated rotation. So what that entails is within the state that's committed to this block, you're going to have the new validator set. Yeah, and essentially just committed to like the state root within this header. So in that case, what we do, or what the operator does, is that it basically has to retrieve this data, and so one other thing that we didn't really touch into this talk is that it is essentially using scale encoding for this data, but it is kind of embedded into a scale encoded array. So basically at this block, you're going to have, so not only the validator set, but you're going to have like a whole bunch of other data. And then this is all like, basically, it is all like scale encoded. So what we've actually done is that we've created a smart contract library that actually will it would actually download all the Avail events, all the Avail event types, and then the defining of how each of them is encoded, and then it actually, so we have a smart contract that essentially like contains all that logic to decode it. Or more specifically, a smart contract library. So basically, so here's like our light client, and then there's the step, and then the rotate function. So at the end of the epoch, our operator will basically take this basically bytes, array of bytes, submit it to the rotate function, which will then call the scale decoding library, and then essentially extract out the new validator set, and then it will save a commitment of that within like the state of the light client. Yeah. So so one thing about our light client, we actually have for every what's called like a I guess validator set ID, and that's like a more substrate like specific terminology. But this light client, in addition to saving all the header information, but also will save the commitment for like essentially all the historical validator sets. Yeah.
No, that makes sense. I mean, that's a smart. I mean, we have to track that.
Yeah.
Yeah. No, so that is cool. That's cool. I think this has been like pretty great. Anything else you wanted to add here?
It's been very pleasurable working with the whole Avail engineering team. But yeah, other than that, it's been a very interesting project.
Cool. So on that last part, like, do any future improvements that you have in mind after this entire thing is first iteration of the development is done, that you have been already thinking of, or I mean, just to share if you're already thinking of something that could be optimized even more.
Yeah, so I think one thing that I think we touched on a bit is just having the like a fleet of signature verification. So that's one thing that's kind of like definitely on our plan. The other thing is that I think we can so we talked about telepathy earlier, but we can essentially kind of help like save essentially gas costs So when we submit like a proof, so we can actually combine like multiple proofs. So let's say the telepathy proof, the Avail proof, and then whatever in the future into one like Groth 16 proof, which would then attest to many different like statements.
Okay.
Yeah. So it should drastically reduce like lower the cost of like submitting these proofs.
Okay. Oh, that makes sense. Cool. So I mean, yeah, just to also let you guys know that once what is the rough development stage at the moment, and what are the next steps to get it to production?
Yeah. So we basically have essentially a pretty well the circuits. We do essentially have all the subcomponents like developed. Right now, we actually do still need to integrate the Stark-based one into it, but is just like it's pretty relatively trivial to do. So once we have that, then that should essentially be kind of quote unquote the final like circuit that we need to build out, and then we'll go ahead get audits and whatnot for that. I think there's a decent amount of like I guess kind of quote unquote cleanup work that we have to do for the operator. But we do have a very early version right now that it is actually live and then posting updates to a smart contract that we have running on Goerli. Yeah, and is also connected to like the Kate testnet right now. Yeah, so that's so just kind of some cleanup work there. We actually still need to. So right now it's just calling step, and then we need to have it called rotate. So right now it's just kind of assuming that it's just basically taking the existing validator right now, but it's pretty close to the end state that we need to get to.
Okay, awesome. Yeah, so I just wanted to also let you know that once we've reached past this stage, we are also planning to post this proof on other EVM compatible L2s as well.
Okay.
So that we can have Avail proof of consensus directly on the L2s as well, because of this newer development where L2s are prioritizing L3s on the stack, and so instead of checking on Ethereum, they could also check directly on L2. So we also plan to deploy this on chains like Arbitrum, Optimism, ZK Sync, ZK EVM, like all EVM compatible chains in general. And actually one thing that maybe Uma we can discuss later is that I've been talking to a few Polkadot folks, and folks in that community also were interested in using this to bridge from a parachain which has grandpa consensus to Ethereum, and vice versa. So yeah, I mean, I think lots of interesting things coming from this collaboration. So yeah, that's it. I think thank you very much, Kevin. Thank you, Uma, for all the sharing so much details about this. Thank you.
Okay, thank you.